This here.
Okay. On the same wavelength. But
I just had it.
I want to be done. That's a cool one. Pretty radical.
So, here. The first thing is, what did we call this diagram here? Can anybody recall what the name of this thing is?
The energy level.
Yeah, this is the energy level diagram, and more specifically, people say it's the orbital energy level diagram. And so all this tells us are the relative energies of the orbitals here. Energy goes up on the y-axis. So the 1s orbital is the lowest energy. Okay, when we have a 1s orbital, it is the lowest energy, but what's going on with the electron? What's going on with the electron in the 1s orbital? And this is well, you have to know, is one, okay, if we have an electron in a 1s orbital, where is it? Well, the Heisenberg uncertainty principle says that it could be anywhere. It could be anywhere, but not anywhere, because there's a certain probability.
95%.
Yeah, we want a 95% probability boundary, which we'll just draw as a circle like this. So this would be the 95% probability boundary. It's not a solid wall, but typically we'll just draw it as a solid circle like that. The Heisenberg uncertainty principle says that we can either pinpoint the position of the electron. If we pinpoint the position, then we don't necessarily know what its energy is, or we can determine the energy. We can determine one or the other precisely, and the other will be uncertain. And so what we do is we pinpoint the energy. If we have a 1s electron, it's here in terms of relative energy. If we pinpoint the energy, so we know what the energy is, then its position isn't so precisely known. So the bird nest analogy usually holds here. So if we pinpoint the electron here, we won't be able to predict where it's going to be in the next instant of time. And so if the electron were here in one instant of time, we don't know what the path it's taking or where it's going to be in the next instant of time. This is one way of visualizing an electron. But what we end up with is we just pinpoint it over a long period of time. If we pinpoint it over a long period of time, what we're going to see is that most of the time it's going to be close to the nucleus. And once in a while we'll see it further from the nucleus. And so what we can do is we can plot this out in what's called, this is called an orbital. An orbital, what that is a probability distribution of where we're going to find that electron. So if we have the nucleus here, right in the center, then the probability distribution peaks right next to the nucleus and then drops off like this. So this would be increasing probability of finding. This would be the distance from the nucleus. Right here. And so it looks something like this. This would be the probability here on the y-axis. So this would be a 1s orbital, and it would be spherically distributed around the nucleus. It looks like that. The next higher energy orbital would be a 2s orbital. The 2s orbital will have a different probability distribution. But again, the highest probability is going to be right next to the nucleus, but there's going to be some probability it's going to be found further from the nucleus. And so 2s can be further out from the nucleus here. And so what we do is we just build up the orbitals on an atom like this. This drawing is going to get a little bit messy, but let's try it. So the lowest energy orbital is going to be the 1s orbital. It's going to be nearest the nucleus, and we'll just draw this as a 95% probability boundary. And then higher in energy, we're going to have the 2s orbital, like this, which will have a greater probability of it being found further from the nucleus. But again, the highest probability is going to be close to the nucleus here. And so that's the 2s. The 2s, if we look at the electron, this is called the electron cloud. All these dots here, which represent finding this. Electron cloud is going to look something like this, where the highest probability is near the nucleus, but with a 2s, it can be found further from the nucleus as well. The 2s is going to show something interesting, though. It's going to have another structural feature. The structural feature is where the wave goes to 0, and that's going to be called a node. And so the 2s orbital has a node, which we aren't going to find any electron probability at that node. And so this is why when I look at the 2s here, it dips down. So the probability is highest near the nucleus, and then it dips down, hits 0 probability here, that's the node, and then increases in probability as we go out. That's where the wave would pass through the axes at that point. Sometimes we do additional things. This is better. This you don't need to know. This is the symbol for the wave function. Wave. The probability is the square of wave function. So normally we might have a wave that starts off with positive, what we call positive amplitude, which is above 0, and then it drops down to negative, and then back up. So something like this. And so sometimes we'll label these, because when we square a negative amplitude here, it turns positive. And so that's called phase information. Sometimes we'll retain it. And so sometimes you'll see the lows marked positive or negative, or colored. They color in different colors that indicate, was a wave positive or negative. You can square it. See here. So this is it. You can see the color code. Like S is all positive amplitude. A P would have, this would be the negative amplitude, and this would be the positive amplitude here. And so they color code it. And so you'll see these two colors indicating what the wave was. Was it above the horizontal or below the horizontal? And then when you square it, you get the probability. And so this is very common. Or they'll use a plus or negative symbol. And so when we look at orbitals, we can see that here. We aren't color coding these. In fact, you don't need to really know this until Chem 1A. Like that. Looks like if you Um, we showed waves earlier. These are the wave functions. This will be a wave function for the 1s orbital. And the orbital itself is the probability, psi squared. The wave function is psi. These are molecular orbitals over here. Let's see. Wave function for atomic orbitals. Here we can see see if this comes out. You see the 1s. This is the wave function in red. And then when we square it, we get the orbital. The square of the wave function is the probability. And the probability is going to be closest to the nucleus, and then the probability is going to approach zero asymptotically. And so what we want to know is the orbitals are infinitely large, except there's minuscule probability of finding an electron out here. And so we'll just do 95% of the area under this curve here, and that's the 95% boundary. And that's what we're going to call the shape of the orbital here. And so, in terms of energy, this is what we need to know. The 1s orbital is going to be the lowest. The 1s orbital is also called what in LLM nomenclature? Yeah, 100 or 100. So our 100 orbitals here, and then that's going to be that. The next higher energy orbital will be 2s. We know that based on the rules for quantum numbers. When you have an n of 1, the max L can be 0, and we go from plus 0 to minus 0. And so this will be the 200 orbital here. It will be that. And then the next higher energy orbital will have a different L, because L equals 0 is allowed, and then L equals 1 is allowed. L equals 1 is called a p orbital. L equals 0 is called an s orbital. For the p orbital, we have 2, 1. And then n, this is NLM. M can vary from minus 1 to plus 1. And so that's going to give us 3 orbitals. These are our 3 2p orbitals. And so if we have an orbital with that energy, it's going to look different. So this will be 1p orbital here. 2p orbital. So an electron can jump from the 2s orbital here, let's say, to the 2p orbital over here. If it does that, then it's going to be slightly higher in energy, and it's going to have this probability distribution. So we're going to see electrons how it mimics this. 2p. Let's take a look at that. Yeah. So it looks like these. These are the 3 2p's. They're all the same energy. They just differ in their orientation. This is all 3 2p orbitals superimposed, overlaid on one on top of the other. And so it could occupy any of these here. We have 3 of those. And then all that means is this. And it's weird because why does it have this shape? Well, it has a different angular momentum. And so this is just the shape it adopts based on the physics of this. And the electron cloud would look something like this. That's just one of the 2p's, and then I can just draw another 2p over here and another 2p over here. And so what you need to know is just that the orbital is the complete description of the electron. do we want to know about the electron? One, we want to know its energy. The energy is going to be precisely known. And so the energy of the electron is precise. However, we also want to know the position. Where is that electron? And how is it moving? Where is it going? Well, do we know that precisely? No. And so what we do is, because of Heisenberg, we can keep one of these precise, the other is going to be uncertain. And so in terms of Heisenberg, this has some uncertainty to this. But it's not completely uncertain, because if we know the 95% chance probability, then that's pretty good. And so we know that a 1s electron isn't necessarily going to be found out here. I mean, it could be found out there, but the probability is exceedingly low. And so 1s electron is typically going to be found within this boundary here. And so it's not totally uncertain. And so what we do here is, for the position, we describe in terms of probability. When we describe it in terms of probability, then there are two ways. We either do the 95% boundary and just draw a solid line. So these would be examples of 95% boundary. This is a solid line representing the 95% boundary. Or we use electron cloud. Electron cloud is like this dot amount or dot density. And so take a look at the electron cloud. You can see the different colors here. The different colors are just positive versus negative amplitude in the wave. The waves will have positive and negative amplitude. So let's look at electron cloud or probability distribution. To the electron cloud here, electron cloud.
So, the mathematical concept of these shapes, are they going to be like in polar coordinates?
Yeah, polar coordinates are usually what they're written in terms of polar coordinates, three-dimensional. Probably the easiest way to represent them. These aren't the greatest. This is not a good one for the electron cloud, because the greatest density of dots typically is near, right next to the nucleus for an s orbital like this. This might be a little better here. This might be a little bit better. You can see you see next to the nucleus there's a greater density of dots, and the further away you get from the nucleus, the dots tend to decrease. This one's good here. And then you can see, you see the 95% boundary dash here? There's still 5% chance finding electron outside. Okay. This is very bizarre. Oh no, this is a single orbital here. This would be like a 2s orbital, but you see right next to the nucleus is the highest density of dots, and then it drops down. And in this region, there's something called a node. A node is zero probability, and then it increases again. So this is like a wave that goes from positive amplitude from 0, and then to negative amplitude, and then back up. So something like this. The actual wave function looks something like this. And we square it. When we square it, then we get this and this. So there's the node. Nodes you don't have to worry about too much, but you can see there are going to be a lot of nodes. There are actually n minus one nodes, internal nodes. And so 3s orbital is going to have 2 nodes inside. Here. So 1s orbital doesn't have any internal nodes. N minus 1 is 0, so 0 internal node. The 2s orbital is 2 minus 1, which is 1 internal node. The internal node, I think, is this black region here. This black region does not represent the high density of dots. It should be a white region. The 3s orbital is going to have 3 minus 1, 2 internal nodes. And so it goes positive amplitude through 0 to negative amplitude, through 0 to positive amplitude. Now, that would be the wave. The nodes don't all have to be spherical. We have planar nodes too. Like in a 2p orbital, that would be a planar node that divides both lobes. This is a 3p orbital. 3p orbital has a planar node right in the middle here and a spherical node, this circle right here. And then we get these shapes depending on the nodes and the lobes. Here. The typical question that asked is, an s orbital, does it have a spherical shape, a dumbbell shape, or clover leaf shape? An s orbital. It would have a spherical shape. Now, S doesn't mean spherical. Interestingly enough, S comes from when they did when they measured the spectrum of the atom, they saw a very sharp peak in the spectrum. So S means sharp. What's that? Well, S means sharp. P means principal. It's a principal peak in the spectrum. D is diffuse. It's a diffuse peak in the spectrum. And so that's where the origin of the SPP comes from. F, then it just goes alphabetical. F, G, H, etc. And so those have no meaning. Okay. So what you need to know is you don't need to know too much. You need to know about the Heisenberg and uncertainty principle. Heisenberg uncertainty principle means we want to know the energy of the electron. So therefore, if we pinpoint the energy, then its position is going to be uncertain and it's going to be described by probability. It's not totally uncertain because we can draw 95% probability boundaries and we can draw electron cloud distribution so we can get an idea of where the electron density is. They call this electron density, depending on where the dots are most dense and least dense. Heisenberg doesn't say this is the way. Heisenberg just says if you know one, then you aren't going to know the other. Or you can know both, but not very precisely. There's a certain limit. And so we could pinpoint the position, but then we won't know what electron that is. So if we pinpoint an electron here, is that a 1s electron? Is that a 2s electron? Is that a 3s electron? Could that be a 2p electron? I don't know. It is. But if we did have a 1s, then we could just, let's say there's only a 1s, we can figure it out. And so this is it. And so we usually come up with little drawings here. 1s orbital, small. That 2s orbital is better and bigger. 2p. Orbitals are like that. X, Y, Z, something like that. And then after the 2p comes what?
3s.
The 3s. But now, when n equals 3, then L equals 0, L equals 1, and L equals 2. So L equals 2, I'll write way over here. So when L equals 0, that's going to be 3, 0, and then our m values go from plus 0 to minus 0, so there's only 1. 3, 0, 0. When n is equal to 3 and L equals 1, so we'll have 3, 1, then we can figure it out. N, 3, L, 1, M goes from -1 to +1. So -1, 0, +1. So that gives us 3 orbitals with 3 different orientations. Now, compared to the n equals 2, the n equals 3 has higher energy, so it's going to be bigger. There's going to be greater probability the electron can be found further away. I'm not going to draw all the nodes in there. Otherwise, it just gets messy. The 3p orbitals are going to be bigger. They have higher energy than the 2p. They're going to have a little bit more complicated shape as well. And then we go here, but things get screwed up because the next higher energy orbital you would expect would be the 3, 2. That would be the next higher energy. You would expect it to be 3, 2. I'm going to draw this up high like this. And so we're going to have 3, 2. Well, if we have 3, 2, it's going to M, 3, L, 2, and then M is going to vary from -2 to, so we're going to get 3, 2, -2, 3, 2, -1, 3, 2, 0, 3, 2, 1, 3, 2, 2. So that gives us 5 orbitals with 5 different orientations. Do you know what we call these orbitals?
The 3D.
Yeah, these are the 3D. These are diffuse, these are big orbitals. The 3D orbitals are going to have these kind of clover leaf type shapes, 4-leaf clovers, etc. Except a weird thing happens here, and this is one other thing you need to know. One, we could generate all the orbitals all the way to n equals infinity. That would be crazy because if you go to n equals infinity, what are your possible L's? So if we're at n equals infinity, the possible L's would be all of them up to infinity -1. You know? So you have a ridiculous number of orbitals when you get high, but we could do something not so crazy. We can go up to let's just do this as a side here. So I can generate all of them. Like if I had n equals 5, what are all the orbitals with n equals 5?
Start with 5s.
Yeah, you start with 5s. So that would be 5, 0, 0, which we call 5s. And then what's after 5s? 5p, which would be 5, 1,
-1.
5, 1,
0.
5, 1.
1.
That would be the 5p. And then you would go to
5D.
5d, which would be 5, 2,
-2.
5, 2,
-1.
5, 2,
0.
5, 2, 5, 2,
2.
2. And so that gives us 5 orbitals with 5 different orientations, and those are the 5d orbitals. And when we have 5f orbitals, it goes s, p, d, f. Well, yeah, because that would be allowed. 5, 3 is allowed, right? So we have 5, 3, -3, 5, 3,
-2.
5, 3,
-1.
5, 3,
0.
5, 3. I'm running out of room here. 5, 3, 2, and 5, 3.
3.
So how many is that? 1, 2, 3, 4, 5, 6, 7. There are 7 5f orbitals, and they have different shapes and different orientations. Are we done? For 5? What's the maximum L? So we had L equals 0, L equals 1, L equals 2, L equals 3, up to a max L of n minus 1. Well, n is 5, minus 1 is 4, so we have one more. We have one more, which I ran out of room here. I'm going to call it the 5, 4. And so it'd be 5, 4. It's one of them. 5, 4. 5, 4. 5, 4. 5, 4. 5, 4. 5, 4. 5, 4. 5, 4. These are called the 5G orbitals. And the 5G, how many are there? There's 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 5G orbitals.
5G.
Yeah. 5G. Well, not the 5G phone, but 5G. 4G doesn't exist in this world. And 3G definitely not. Okay, what about 5H? Would you expect 5H orbitals to exist? No, because that would violate what? That would violate n minus 1, which would violate what? Where does the n minus 1 come from? What was the name of that equation? Or the person? So Schrodinger equation, that would violate the Schrodinger equation. And that would be called forbidden. 5, 5 is forbidden. And so the max L is n minus 1. But we can have all of them, 0, 1, 2, 3, 4, up to the max. And the max is this. There are more mathematical patterns. You know, this would be something you'd see in Chem 1A. How many total orbitals are there? Well, actually, 35 is too high. Close. 25. How many total orbitals are here in the n equals 3? 9. How many total orbitals in n equals 2? How many total orbitals in n equals 1? Do you see the pattern? What is the pattern? Yeah, it's n squared. There's going to be n squared orbitals for each n. So it gets crazy. If you go to n equals 10, how many total orbitals are there? 100. If you go to n equals 1,000, there can be 1,000 times 1,000, 10 to the third times 10 to the third, which gives you 10 to the sixth. They're going to be 1,000,000. Could you figure them out? Yeah, you could figure them out. It's just going to take time, right? But it'd be easy to figure out because we figure them out just like we did here. It'd be pretty straightforward. The other thing is, do you see another pattern here? Yeah. Or there's the other way of doing that is, how many orbitals in the D? 5. How many orbitals in the F? 7. How many orbitals in the G? 9. The other way of doing it is this. Rather than go up by 2, what if I did the Z? How many orbitals in the Z? Do you want to sit there and count them, or do you want some mathematical pattern that we could use to figure it out? Yeah, mathematical pattern. And so the number of orbitals for a given L there are 2L plus 1 orbitals in what we call, L is called the sublevel or the subshell. And so this is the L equals 0 subshell or sublevel. Etc. This is the L equals 1 subshell. So that we have the S subshell, the P subshell, the D subshell. If we had the Z subshell, we could figure it out. It's just 2L plus 1 orbitals in there. And so we just got to figure out what is the number for Z, and then we just write it all out, and we can figure it out.
So wait, there are 2L plus 1 orbitals in what?
In each subshell. So let's go to this 5s subshell. How many orbitals are there? Well, it's 2L, L's 0, so 2 times 0 is 0 plus 1 is 1 orbital. In the 5p, how many orbitals are there? There's 2L, L's 1, so 2 times 1 is 2 plus 1 is 3. I mean, you could see the pattern visually. The pattern visually is, you know, you add the negative, it's 2L because you're going from negative to positive, and then the plus 1's including 0. So 2L, you're going from negative to positive, and the plus 1 is the 0. So there's 2 over here, 2 over here, so that's 2 times 2 is 4, plus 1 is 5. The same thing here. If we go to the 5G, we got 1, 2, 3, 4 on this side, plus 4 on this side, so it's 2L. 2 times 4 is 8, plus 1 is 9 for G. There are other mathematical patterns in there. We're not going to, you don't have to worry about this mathematical pattern, but you can see we can generate the table. It's not hard to generate this table. Problem is we just screwed up the energy here, because this is not the observed energy. It goes 1s, 2s, 2p, 3s, 3p, but it doesn't go to 3d. Where does it go? It goes to the 4s. And so the next higher energy, so the 4s is actually lower in energy than 3d. And so it goes 4s, which would be 400. And then it goes to 3d, and then it goes to 4p. 4, 1, negative 1, 4, 1, 0, 4, 1, 1. That's our 4p. And then it should, after 4p, it should go to 4d. But the 4d turn out to be in the next shell. And so the 4d, and then after 4d, we should have 4f. But will we have 4g? We won't have 4g because that violates the mathematical pattern which is needed to satisfy the Schrodinger equation. And so what's more useful for us is not doing this because we don't know what the energies are here. But there's a quick, easy way to determine what the energies are. You know how we determine that? We use a little energy pyramid to do that. What does it look like? You have the 1s, 2s, 2p, 3s, 3p, 3d. The same thing here, L equals 0, L equals 1, L equals 2. So when n equals 3, the max L is 2. And then we go to 4s, 4p, 4d, 4f. 4f because L equals 3 would be the max L when n equals 4. And so we just add one more step each time. 5s, 5p, 5d, 5f, 5g. And we just wrote out all the orbitals there.
I'm trying to find in the book, but I vaguely remember it talking about there's an area where the pattern breaks on the periodic table. I think it's after like copper or something like that. There's a break in the pattern and it.
Yeah. There were some exceptions, you know. As you go higher and higher in energy, what happens to the spacing between the orbitals? It becomes bigger or it becomes smaller? It actually becomes smaller. And if the spacing becomes smaller, then there could be exceptions where electrons should be here. Aufbau says it should fill below us, but it's just slightly higher in energy, so it could be there, depending. We'll take a look at a couple of exceptions that you need to know. but that's for filling. Each shell starts with an S. So this would be the first shell. Okay, the next shell starts with the S, and it's going to end here. This would be the second shell. The third shell starts with 3S, and then ends here. This would be the third shell. The fourth shell starts with 4S, and it's going to go 3D, 4P, and then stop here. This would be the fourth shell. The fifth shell, what would the fifth shell look like? It'd start with 5S, and then go to 4D, 5P, and then stop, because we're here at 6S. And so this would be the fifth shell. The sixth shell starts with 6S and then goes what?
4F, 5D, 6P.
Yeah, 4F, 5D, 6P. And then stop there. That will be the sixth shell. The seventh shell would go 7S,
5F,
5F, 6D,
7P.
6D, 7P. Good. Well, it turns out, okay, these are our shells, but you know what? We don't have to memorize this, or we don't really have to figure this out. But we can figure out, if I ask you what the 10th shell consists of, could you figure it out? Sure, you just have to extend the table down, right? We really don't have to do this because you know why we don't have to do this? We don't have to do this because the periodic table is arranged in terms of shells. So, you know, up through the seventh shell, it's there. The first shell is the first row here. This is the first shell. And the first shell can hold up to how many electrons? 2 electrons because of, what was the exclusion principle? Whose exclusion principle was that? You don't necessarily need to know the names for everybody, but this one you need to know. Pauli exclusion principle. And so hydrogen is 1 electron, then helium fills that shell. Once we fill the first shell, then we have to jump up to the next shell, which would be the n equals, well, the second shell. We don't call it n equals 2 necessarily because all the n's get mixed up. When we get to n equals 3, then some of the orbitals are here in the third shell, but this orbital is up here in the fourth shell. We just call it the third shell. And so to fill up the second shell, it's going to take, well, the S takes 2 electrons, so this would be lithium and beryllium. And then we go up across boron, carbon, nitrogen, oxygen, chlorine, neon. So once we get to neon, we filled up the second shell. The third shell consists of 3s and 3p. The fourth shell goes 4s, and then what? 3d, and then 4p. So we don't need this. I mean, if we have the periodic table, we can see it. This is the fourth shell. It goes 4s, 3d, 4p. And so you shouldn't get this wrong, hopefully. Even though you shouldn't get this wrong, lots of people get this wrong and screw this sequence up here. They go 3s, 3p, 3d. That's not what it does. It doesn't go 3s, 3p, 3d. It goes 4s, 3d. The fifth shell is similar. It goes 5s, 4d, 5p. But the sixth shell is different. The sixth shell does what? Well, let's take a look at the sixth shell. The sixth shell should go 6s to 4f to 5d to 6p. Now, the problem is this 4f, how many orbitals are there? There's 7 orbitals, which is 14 electrons to fill that. There's 14 boxes for 14 electrons. What they did was they didn't want to spread this apart to make room for the 4f. The 4f should go here, right? So it should go 6s, 4f, 5d, 6p. So it's run out of room. You can see this in the periodic table if you look at the numbers. And so let's take a look at the numbers in the periodic table here. The atomic numbers. Right? Copy that periodic table. So when we go to the sixth shell, take a look. You see 55 here? It goes 55, 56, 57, and then it drops down here. This is 58. So it goes 55, 56, 57, 58. And then it goes through here. Here's 71. I'm sorry, 71. We go back up to 72 here. So this has been broken to try to accommodate the F for the sixth shell. The seventh shell does the same thing. The seventh shell is going to have it's going to go 7s to 5f. And so it goes 7s to 5f, which are down here. And so we use the numbers to help us out with this. Other periodic tables will have other ways of indicating this. If you look at the periodic table here, we're at the sixth shell, so it's going to go 6s, and then do you see the double asterisk here? Double asterisk means go down here to the lanthanides. That's double asterisk. And then do you see this upside down triangle here? It means drop down to the actinides here. And then you can get your F shell filled, and then go back up and fill the D shell. Does that make sense? And so then you want to make the periodic table too long with these in there. So that's why you might get confused. But you shouldn't get confused if you just follow the numbers. Now, not everything fills perfectly. There are some exceptions in there. So this is what we predict. Theoretically, this is what we predict. Well, experimentally, we observe certain things. It depends on how strong the prediction is. You should be able to predict these things as well, if your theory is good. But some of the calculations for quantum mechanics are very difficult. And so the math is very difficult there. So this is generating this, and all these orbitals are going to describe the energy precisely. And this is why we have an energy level diagram, because we want to describe the energies of these orbitals, the orbitals with loud state with electron, precisely. And then we have some kind of drawing for the position or the probability of finding that. And so one thing is, you should know how to draw this energy level diagram. Either memorize it or do whatever. It's going to go 1s, 2s to what?
2p,
To 2p, to
3s,
3s, to 3p. We're just going along on the periodic table. I mean, if you go back to the periodic table, you can just follow along. Did I use that? Three S to the 3P to what? To the 4S
3d,
to the 3D to the
4p,
4P, etc. This will go all the way up to n equals infinity. N equals infinity is not infinite energy. So the orbitals are just going to compress that. You should know this, the first 4 rows or the first first 4 shells. You should know the periodic table. And you should know the energy level diagram here. All right, now when we fill these, we use the off bow and poly and what was the other one? Off bow says fill the lowest energy. Poly says no more than 2 electrons with opposing spin. And Huns. Huns doesn't apply here, but Huns will apply here. How do I fill these? With parallel spin. And then we'll have to do, how many electrons is this? This is 2, 4, 5, 6, 7. What has 7 electrons? Nitrogen. So this would be the element nitrogen. And then with oxygen, what do we have to do? Yeah, we have to pair. So this would be oxygen, this would be fluorine, and then neon. And then sodium, magnesium, then what? Aluminum,
yeah,
and then silicon, chlorine, argon. So argon. Argon has a total of 18 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons to argon. 18 electrons will fill the first 3 shells. Neon has a total of 10 electrons, which will fill the first 2 shells, and helium has a total of 2 electrons, which fills the first shell. Now we're going to fill the 4th shell. And so below sodium is potassium. Potassium is going to have 1 electron in the 4s, and then calcium, and then scandium, titanium, vanadium, chromium. Okay, I'm going to stop here.
That's where it breaks.
That's where we have an exception. So this is a lot to write, and so there's shorthand ways of representing this. This is called a orbital energy level diagram, and it's going to be the most information, but it takes up a lot of space. We have another type of diagram, which is called the orbital box diagram. The orbital box diagram doesn't take as much space vertically. What you do in an orbital box diagram is you represent the orbitals like this, with a box. 1s, 2s, 2p, which has 3, 3s, 3p, 4s, 3d, 4p, And then you fill the boxes with electrons. Represented by arrows. And then this will be chromium. This chromium has 24 electrons, so it should have a total of 24 electrons on arrows. 24 electrons. That's the orbital box diagram. It takes up less space. And so we lose a little bit of information about relative energies because of the gap. There's a bigger gap between 1s and 2s. We have a bigger jump here. And then the jumps decrease magnitude. There's an even more compact way of writing this, and this is called the electron configuration. And so here we do 1s2. The superscript 2 represents not squaring the s orbital. It represents that we have a 1s orbital with 2 electrons in there. And then we have a 2s2. And then we label these. Each of these 3 p orbitals differ based on the axis. And so there's going to be an x, 2px with 2 electrons, a 2py with 2 electrons, and a 2pz with 2 electrons. And then we'll have 3s2, and then a 3px with 2 electrons, and 3py with 2 electrons, and a 3pz with 2 electrons. And then we'll have 4s with 2 electrons. And then we're going to have 3d. Now the 3ds, they have plane notations on there. So we look at the xy plane, and the clover leaf is going to be in the xy plane. That's going to have 2 electrons, 3dxy. 3dxz for the xz plane, that's going to have 2 electrons. 3dxy, xz would be next. YZ, 3dyz with 2 electrons. And so we got those 3 planes in 3 dimensions. And then there's something called the 3d x squared minus y squared, which has a slightly twisted orientation compared to the xy. And then we have the 3dz squared. And so we just pick one. Actually, these are going to have 1. Sorry, this is going to have 1, 1. This is Hund's rule. We fill them singly. Sometimes d squared, dz squared doesn't have an electron in here, so this is 0. Let's write 0 there. It's empty. The 4p's are also empty. Right? The 4px is empty. 4p y is empty, and the 4pz is empty. They're empty in what we call the ground state. The electrons can get excited and populate the 4p in all the higher energy orbitals as well. There are a whole bunch of infinite number of higher energy orbitals that can get populated and they'd be excited. So this would be the ground state, the lowest energy configuration. But, you know, it becomes a bit of a pain to write these individual orbitals out. And so what people do is they just combine this. So, for example, they'll do 1s2, 2s2, and then they'll combine all 3 2p's. And so this will be 2p246. They'll call it 2p6 to show that we know that all the p orbitals can hold a max of 6 electrons. So we'll just combine it to 2p6, 3s2, 3p6, 4s2, 3d. Now there are only 4 electrons in the 3d. This would be chromium, 24 electrons. And so this is the expected. This is the expected energy level diagram, which shows the most, although we don't, I didn't draw the pictures of the orbitals here. The energy level diagram, which shows the most information. followed by the orbital box. We lose a little bit of information, but we save a little bit of room. Followed by the electron configuration. This is the condensed, this is the expanded electron configuration. Typically, people write the condensed electron configuration. But this becomes a bear too to deal with. And so what we see is the first shell's filled helium, second shell's filled neon, third shell's filled argon. And so what people do is they try to condense this even more. First shell's filled, second shell's filled, third shell's filled. Third shell's filled up to argon. So we call this the argon core. And then we're going to have 4s2, 3d4, meaning which we have a partially filled fourth shell here. And so these are three ways of writing the electron configuration, from the expanded to the condensed to using what we call the Nobel gas electron core abbreviation to this. However, this is not what's observed. Right on here. What's observed is this 4s electron gets promoted to 3d. So this 4s electron here gets promoted to the 3d. Same thing here. We're going to cut this down to 1 and then promote it here. 1. This only happens for chromium so far. And change this to 5. This is going to go 1, 5. Same thing here. It's going to go 1, 5.
Does this happen for like chromium and everything after, or
No.
just specific one?
Yeah, this specific one. So we'll take a look at why it's done this right now. So I'm going to use the abbreviations for this. We'll start off with scandium. Scandium is normal. If I'm going to use argon, I'm going to use the abbreviation, but I'm going to use the orbital energy level diagram. So we go to argon up to here, and then we go to 4s, and then we go to 3d over here, a little higher in energy. And then we go to 4p, a little higher in energy over here. So scandium's normal. Scandium goes like this, 4s, 2, 3d, 1. And so the electron configuration for scandium is we write argon, 4s2, 3d1. Yeah.
Do we put the 1, or do we always put the 1, or do we leave it?
No, if you leave it blank, then it could be empty.
Okay.
We have to put the 1 there. There's another way we write this. Or we write this argon, 3d1, 4s2. This is a pattern. If we have a 1s orbital, let's say it's this big, about how much bigger is a 2s orbital? A 2s orbital is going to be about 4 times bigger. 4 times bigger than a 1s. If we go to 3s orbital, the 3s orbital is about 9 times bigger than a 1s orbital. So 4 times bigger than 1s, 9 times bigger than a 1s. If we go to a 4s is, do you know how many times bigger? 16 times bigger. So this is a big orbital. The 3Ds, what's bigger, a 3D orbital or a 4s orbital? You think a 3D orbital is bigger because it's higher in energy, but it's not because of the way the distribution is. And so although the 3D has higher in energy, the 4s is a lot bigger. There's reasons for that, which we're not going to really get into. It has to do with the probability. There's a much higher probability that a 4s electron will be found next to the nucleus than a 3D electron. That's the reason why. But there's also a greater probability a 4s electron will be found further from the nucleus, and all the other, it does this, like this. And so sometimes we write it like this. We call these the inner electrons, and we call this the outer electron. The outer electron is going to have the highest N. The highest N is going to give us the biggest orbital, which is going to be the one that's most probable in finding it furthest from the nucleus. So highest N. So the inner electrons, these are called the core electrons. And the outer electron is called the valence electron. So titanium has one valence electron. Not titanium, sorry, scandium. Scandium has actually not one. How many valence electrons does scandium have? 2 valence electrons. So think about this. If you're an oxidizer, which electron will you attack first? If you're an oxidizer, will you grab one that's at the D? Electrons is 9 times bigger than the S. Or would you grab, this is the 3D, or would you grab the 4s? You're an oxidizer. You're coming along to take an electron from scandium. Are you going to grab a 4s electron, or are you going to dig deeper and grab a 3D electron? You're going to grab a 4s electron. In fact, scandium has how many 4s electrons? 2 4s electrons. So if you're an oxidizer and you want 2 electrons, you're going to take both of the 4s electrons. If you take both of the 4s electrons, then that leaves scandium with 2 electrons missing, 2 negative charges missing. It's going to leave scandium with a +2 charge. Well, once you strip off the 4s electron, and let's say you're still hungry for electrons. If you're still hungry for electrons, what's the next electron you're going to attack? 3D. So if you take that 3D, then that gives scandium a +3. So the 2 charges you'd expect for scandium are +2 and +3. But for scandium, it's very easy to take all 3. +3 is not too terrible to form. It turns out scandium's fixed charge at +3. Scandium's fixed charge at +3 because we can take these. We'll take the valence electron, and then we'll take one of the inner electrons, and that's going to be the D. However, we're not going to take the argon, because the argon, that's all filled shells. And if we take those, it'll destabilize things. Okay, after scandium comes titanium. So titanium is going to have 2 valence electrons, and then these Ds should be in the inner shell. And so the common charge for titanium, if you're an oxidizer, you come, which electrons will you take first? The 4s followed by the 3D. And so for titanium, the two electron configurations are going to be like this. It's going to be argon, and we have it filled, 4s2, 3d2, or argon, 3d2, 4s2. The second one shows the relative distance kind of thing. And so this is going to show the valence, the outermost, versus the inner. So titanium, a common charge might be +2. An oxidizer comes along and strips off the 4s electrons. Or +4 if the oxidizer can take those 3 Ds, too. In fact, titanium +4 is quite common, but it's hard to get a +4 charge. So that's titanium, and then we go to vanadium. Vanadium is going to have another electron here. And so this is going to be argon, 4s2, 3d3, or argon, 4s2, 3d, oh no, that's wrong. Sorry, 3d3, 4s2. So for vanadium, an oxidizer comes along, strips off these 2 electrons, that gives us +2. And then it tries again to take another electron, that will give us +3. And if it's really successful, we could get +4 or maybe even +5. But it's getting harder and harder because the more positive charge you have, the harder it is. So these are filled normally. It's just kind of weird because there are 2 ways of writing this. Inner versus outer. Outer shell is, it's not necessarily shell, but outer could be outermost electron, we call the valence. And the outermost electron that's defined by the highest N. So that's vanadium. Then when we get chromium, we expect this. For chromium, we expect argon, 4s2, 3d4. But what's observed is this. What's observed is argon, 4s1, 3d5. Let's say you have a cake. If you have, you could either think of you have half a cake or a half empty cake. So let's say you had something like this. This would be a half filled D sub-level or sub-shell. A half-filled D sublevel or subshell has some symmetry stability to it. Let's just say additional stability. And so if you had something like this, there's 2 ways to cut this in half. One way is just cut it in half and then give half of it away like this. The other way of cutting it is like, let's say I had a cake and I cut it, instead of cutting it in half like this, I cut it in half like this. And then give the top half to somebody. You see how I retain the symmetry of the cake? If I cut it like this. And so this way is like this. If I have 5 d orbitals, I fill half of them. Like that. And so that's that. Is that very stable? No. This way is if I have 5 d orbitals and I fill them up halfway, then the picture I get looks like this. I have that full symmetry that is all the d orbitals. When you add up all the d orbitals, it has what we call spherical symmetry. And so I add up all the d orbitals and cut it in half like this. This is half filled, not half the cake like this. Well, this half filled has additional symmetry, which is what we call spherical symmetry, which adds to a little bit of stability. And so what I end up with is I end up with something like this. I end up with 4 d electrons and 1 empty. So this is like this half filled with one slice taken out. So it sure would be nice to not have that slice taken out. It sure would be nice just to have a half filled or half, half layer. This is a 2-layer cake. It sure would be nice to have one layer complete for that cake. And so this is what happens. What happens is we can get that, by taking one of the S. And so this is the 4S, this is 3D. We're just one slice missing. So we'll just take this electron, promote it up to here. That's going to cost energy. How much energy does it cost? It costs this much energy. But what you get in return is you filled that first layer. Once you fill that first layer, then that gives you additional stability. And so it lowers the energy. And so it turns out that this is energetically favorable. However, if we're 2 electrons shy, like this is 3D3. So 3D3 is going to have 2 slices removed. And you go, wow, I really want the full without these 2 slices remaining. So could I promote these 2 electrons here, the 4s electrons, to half fill that D? So rather than having 3D3 where 2 slices are missing here, I'll have 3D5 where I get the first layer all filled. Well, that's going to cost too much energy. And so it doesn't happen here. We're not going to promote 2 electrons here. But it turns out if we only have to promote 1 electron, then it's okay. We can promote 1 electron to fill that. Does that make sense?
Why is it favorable? Do they gain something from having the?
Yeah, they gain something in stability when you look at the electron cloud. Gain something having that symmetry, the spherical symmetry.
So would that be energetically favorable for everything in column 6?
Yes.
So we're going to follow that pattern in column 6?
Yeah, except the situation is, as the orbitals get bigger and bigger, it becomes less and less significant. That is, it's not. So what we can see is, actually, let's see. So you would expect the same. So what's below chromium? Below chromium is MO. Do you know what MO is? No, molybdenum. 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 So if you look here, do you see the electron configuration? Except they do this kind of weird. Rather than using superscripts, they're using subscripts. But take a look at what happens here. Molybdenum should be krypton, 5s2, 4d4. But what happened? The s electron gets promoted to a d electron to half fill the subshell. And so that worked out. Okay, what's below molybdenum? Tungsten. So let's take a look at tungsten. So tungsten should do the same thing as molybdenum. Let's take a look and see. Okay. So tungsten's below molybdenum, it should do the same thing. In other words, we should promote an s electron to half fill the d, but did we? No. So it becomes less significant. I mean, when you look at the 5D are huge. And so it becomes less of an issue, when you got these gigantic orbitals. They're so gigantic that everything's pretty diffuse anyway, as far as spread out. But I mean, there are other arguments for this to do, but in this case, it's different. So here, if you want to read more about this, there's this. Why does tungsten not kick up an electron from S sublevel like you'd expect? You'd expect it to kick up an electron. Let's see what they say. I don't know. This is not a published thing. Do you have to know this? No, you don't have to know this.
That's not a handle.
So chromium and aluminum behave as you'd expect. There are a lot more exceptions when you get further down in the periodic table on how the orbitals fill. In fact, we'll see. Let's take a look at. We'll take a look at the next exception. So after chromium comes what? Manganese. So let's take a look at manganese. Manganese, we'll look at argon. We're going to have 4s2, followed by 3d5. So we don't have to promote any electron here. It's already half filled, so we're good. And so manganese is going to be argon, 4s2, 3d5, or argon, 3d5, 4s2. So what are the common charges of manganese? +2, +3. So +2, we remove the 4s. Those are going to be the easiest accessible electrons because they're going to be the furthest, the biggest orbital. And then we're going to attack this. But when we attack this, we're going to disrupt this symmetry. So this is going to cost us a little bit more energy. And so manganese +2 should be common, and manganese 3 I would expect to be less common because we got to disrupt this. But what about manganese 4? Well, the +4 is getting more and more difficult, +5, +6, etc. It's getting more and more difficult to ionize. So +2, +3, maybe take one of the d electrons. So manganese +2 probably more common than manganese +3 is my guess. And then after manganese comes what?
Iron.
Iron? Okay. Iron. Iron is 4s, 2, 3d, it's 4 p's are empty. 3d, 6. 1, 2, 3, 4, 5, 6. Which gives us an electron configuration of argon, 4s2, 3d6, 4 argon, 3d6, 4s2. So what are the common charges of iron? +2, +3. In this case, however, I would expect +3 to be more common than +2. +2, we knock out this one, and then +3, we take one of these, which results in a half filled. +4, would you expect that to be as common? No. +3, yeah, because what we have here is we have something called electron-electron repulsions occur, and that could help us. Okay, after iron comes cobalt. So let's do cobalt next here. Which would be 4s2, 3d7, right? 1, 2, 3, 4, 5, 6, 7. For argon, 3d7, 4s2. That's fine. +2, +3 is common for this. You would expect maybe +4, but it's getting harder to ionize. After cobalt comes nickel. Nickel is argon, 4s2, 3d8. Do you see something? Nickel is 2 electrons away from filling the D. If we can fill the D, then it has that symmetry. When you add up all the D's, it's what we call spherically symmetric. It's like D. But it costs too much energy. To promote 2 electrons to fill this, so we have a 2-layer cake now. To fill that would be not cost effective, so it doesn't happen. And so nickel's this. It would just be argon, 4s2, 3d8, or argon, 3d8, 4s2. Okay, then after nickel comes copper. So let's take a look at copper next here. Copper should be argon, 4s2, 3d9. 4 p's are empty. Okay, what do you see here?
Just a quick question. So everything from here on out is going to be an argon core, where before in the earlier of the periodic table, it's going to be a neon core.
Mm-hmm.
Okay. Why is that?
Yeah.
It's just a shorthand for having it right out.
Yeah, no, I get that. It was just trying to understand why one is neon.
Well, anything you describe in the second row will be helium. Anything you describe in the third row or the third shell will be neon core. We're in the fourth shell, so everything's going to be argon core. In the fifth shell, everything's going to be krypton core.
Got it.
What do you see? You know what I see here? I see 1 electron shy of having the filled 2-layer cake. So if it's only 1 electron, then it's worth it. And so 1 electron is going to get promoted here, and then we're going to fill this completely. And so what we expect for copper is this. We expect it to go argon, 4s1, 3d10. Or argon, 3d10, 4s1. Now, copper, I expect +1 to be the most common. +1 should, and in fact, I only expect +1. I only expect +1 for copper because I don't want to screw up this. Do you want to take a slice of, you want to leave the cake pristine, right?
Yeah.
And so +1 gives me this for copper if I lose that. But +1 is not the most common charge for copper. What's the most common charge? +2. And so there's another reason why D9 is special. D9 is special, but you won't learn about it until Chem 1B. And so don't worry about it now. After copper comes what? Zinc. Zinc, we don't have to do any of this promotion stuff because zinc is going to be argon, 4s2, 3d10. And then 4p. So here, when we look at zinc, we would go argon, 4s2, 3d10, or we rewrite this to show inner and outer. So it's going to be argon, 3d10, 4s2. What do you think the most common charge for zinc is? +2. Do you see +3 for zinc? No. And so zinc can lose these. This will be the outermost electrons, and loses that, and then retains this. So zinc is fixed charge to +2 only. Okay, what comes after zinc? Gallium. So let's take a look at gallium. Gallium is going to be argon, 4s2, 3d10, 4p1. Yeah. And so when we write the electron configuration, we write it like this: argon, 4s2, 3d10, 4p1. But what we want to do is we want to show the inner versus the outer based on the size or the dimensions of this. And so this is going to be rewritten argon, 3d10, 4s2, 4p1. These orbitals are 16 times bigger. So these are what we call the core or the inner shell electrons. And this will be the outer here. And so what do you think the common charge for gallium is? Yeah, we probably +1 plus 3, +1 or +3. In fact, it's easy to take all three of these. So the common charge for gallium is +3 as it takes these. These outer ones are called the valence. And so this has 3 valence electrons, and the inner ones are called core. So we have core and valence.
Why is 4s2 also valence? Like I would just think that only OP1 would be valence.
Because they're all about the same size.
They're all 16.
Yeah. So it's going to take the 4p first. There are 3 of them. 3 orbitals it can take it. This is going to take 1. Boom. Takes that. A little easier to pull off, and then it'll take the 4s. Those are big. After gallium comes germanium. I've been going nonstop. We'll take a break here. Yeah, we'll take a break now.